Welcome to part 2 of chapter 8. In this segment, we're going to start looking a little bit closer at collisions. And you have to remember, in a collision, momentum is conserved. Momentum is just mass times velocity. And so momentum conservation means the total momentum of all the objects before the collision added up equals the total momentum of all the objects after the collision. So we start looking at that in more detail. We start looking at the collision of two objects. Here we got a mass coming in. Mass, think it was a billiard ball. If you ever played pool, you actually know a lot about conservation momentum. And so we got this ball that comes in, hits this other ball. It goes off this way, and the other ball goes off that way. And so since momentum is a vector, we have to break all of these pieces down into their vectors. Right? So P1x, right? This is P1, P1x plus P2x equals P1x prime plus P2x prime. And P1y, which is 0, right? Plus P2y, all right, which is 0 because P2x and P2y are 0 before we start out here. And P1y prime, all right, the y component up this way, and P2y prime, the y component down this way, all add up, right? So the momentum in x, this momentum plus the momentum of that, which is 0 because it's sitting still, has to equal the x component of this momentum afterwards, right? And the x component of that momentum afterwards. So if we start breaking down the momentum of this into two pieces, and then breaking down the momentum of this into two pieces, right, like that. That's what we're after, is getting these pieces together so that they add up to be the same as that. So one thing that pops out right away looking at this is, since there's no y component before we start, right, before the collision, there's no y component to the momentum. That means since these are both 0, these have to add to 0. And in fact, that means this vector up, that component of the vector up, and that component of the vector down are equal and opposite to each other, right? Very simple part of conservation of linear momentum, right? Because it's a vector, these pieces up and down end up canceling because we had no y component to begin with, right? So if we look at this a little bit more then in terms of the numbers we had this was 0 altogether at the beginning. All right, momentum of M2 was 0 altogether at the beginning, so we have M1 V1. So M1 V1 prime after the fact, cosine theta 1, and M2 V2 prime cosine theta 2, and then we have a second equation, with the cosine here, with the sines, right? So the x components all add up. The y components all add up, all right? And this set of equations is the result of working through this collision, all right? Now, look at the number of unknowns we have, right? We have V1 prime, V2 prime, theta 1, and theta 2. You need more information about this than just your starting condition to figure out what the answer was. There are a few too many unknowns here. Okay, another place where momentum comes into play. That's in rocketry, right? Rockets use conservation of momentum, all right, to propel themselves by giving momentum to the exhaust, right? Since momentum has to be conserved. If you start off with the rocket with no exhaust coming out and the total momentum is 0, and then the exhaust starts coming out, well, the rocket gets momentum that cancels out the exhaust momentum so that the total momentum remains 0. All right? Total momentum remains 0. Now, one of the things we've done in recent years with probes, and it's one of the reasons that our probes are so much better at going different places and visiting multiple places much better than they were in the past, is that we now have what we call ion drives that get the exhaust up to 20 to 50 kilometers per second, right? Per second. So the exhaust has really high momentum for its mass, and that means you don't have to have as much exhaust to get the get the probe moving, right? So in the end, what does this mean? The acceleration of a rocket, all right, is given by the velocity of the exhaust divided by the mass of the rocket times delta m over delta t. This quantity, delta m over delta t, is the rate at which mass is going out the exhaust. That's really all it is. It's the rate at which mass is going out the exhaust. All right? So that's basically what that term means, that we're losing a kilogram a second out the exhaust or a gram a second out the exhaust, right? And then the final term is that's the acceleration if you were in free space with no gravitational field, but we have to add in the fact that, the Earth's trying to hold on to you, so you have to subtract the acceleration of gravity of the Earth. All right, quick review. Collisions, right? We add up the momentum in each direction. Once for this problem, it kind of looks like this when we put in some of the values, right? Momentum's a vector, so the x components have to add up before and after, and the y components have to add up before and after to be the same. If it's an elastic collision, then kinetic energy is also conserved, and kinetic energy before and kinetic energy afterwards is the same. And finally, a rocket propels itself along through conservation of momentum. And the acceleration you get is proportional to the velocity of the exhaust, VE, divided by the mass of the ship, right? Times the rate at which mass is going out through the exhaust, delta m over delta t, minus the acceleration of gravity. All right, that's it for Chapter 8.